So today we're going to continue with our look at composite systems with the partial trace. So again, suppose we have a composite system A, B. Okay, so A is a set of some quantum particles, and sitting next to them is another set, B, of quantum particles, and let rho AB, denoted like that, be the density operator describing the system. Density operator. And what we want to do is have a description. What the partial trace allows us to do is have a description of just one of those systems. So just of what the system looks like if you only have the A particles. Okay, so let me think. So how should we define this? So this is like the partial trace. Well, I'll give you the definition and then we'll look at some examples. And I think with the examples you'll see, oh yeah, of course, that's the way to do it. So the partial trace over the system B and this partial trace we just denote with, let's say, a trace with a sub-indice B. So what's a typical term? I'm just going to tell you what to do to a typical term in the density operator, and then everything will be extended linearly. So a typical term here would be something like, so the bra is composite, so we have an A and a B, and then the ket as well. And the trace over B is simply you ignore the A's and you trace the B's. So you just do a normal trace them over the B system. For one term, and then extend this linearly. Okay, so let's have a look at some examples. Here we have psi. This is defined on a 3-bit system. So that's 0, 1, 0, 1, 1. I thought I'd be a bit inventive and put some complex coefficients in there. 2, 1. Now, to make this a unit vector and a valid quantum state, I need to norm this. So this is going to be 1 squared plus 1 squared plus 2 squared, which is 6. So I need to put 1 divided by square root of 6, so that it has unit distance 1. Okay, so that's a state in the quantum state, and then the pure state density operator will be this. Okay, so rho looks like this, and this would be then 1 over 6, so we're going to get 9 terms. And I'm going to write them out just because once you've seen this one example, a couple of examples, you'll never be worried about a partial trace again. Okay, so just bear with me, so it won't take very long. So this is this bra with the kets going the other way. So this when I get to this one, it's going to be minus 2i 0, 1, 0, 0, 1, 1. Okay, because this is gone around the other way. It's been transposed. Plus, and now we've got the 1, 1, 1s. 0, 1, 0. 1, 1, 1, 1, 1, and again minus 2i 1, 1, 1, 0, 1, 1. And finally, the plus 2i 0, 1, 1, 0, 1, 0, plus 2i 0, 1, 1. So difficult to do. 1, 1, 1. And that is going to be plus 4, 0, 1, 1, 0, 1, 1. Okay, so that's our 9 terms in the density operator row, and this is what's called a pure state. Okay, so it's a bit confusing because this is a state, this is a density operator, which is a rank 1 density operator. It's a ket bra of this state, and we call it a pure state because it's not a, well, we'll see an example of a mixed state in a minute. Because it's simply a ket bra. So now, let us calculate the composite system, the partial trace. So I'm going to fix a composite system here. Let's say that A is the 1, 2 system. And B is the 3 system. So in our 3 qubits, Alice has the first 2, Bob has the third one. And so how should Alice view her system? So this is row A, which is going to be the trace over B of row AB. So this is row AB. And we're going to trace over B. So we fix an orthonormal basis for the 3rd qubit. Okay, well, just to make our lives easier, we might as well take the computational basis. So that's going to just be 0 and 1 in the 3rd qubit, and we trace. And recall that the trace, so if we were doing the trace over some basis, so the trace of something is the sum of A, and this A goes over an ortho A in an orthonormal basis. Okay, so oops. So let's just remember that. So that would be just a full trace, and here we're just tracing the 3rd qubit. Okay, so we've got to trace over the 0s and 1s. So that means that we have to look at the 3rd qubit and decide whether we trace whether this is still going to be there. So if I'm coming from 0 from one side and 0 from the other side, then that's good, because here I'm going to be left with the 0, 1, the 0, 1. So this is going to be, so this is going to give me a 0, 1, 0, 1. Okay, now here I get 0. I need a 0 coming from this side and a 1 coming from this side, which I don't have because I have 0, 0 or 1, 1 coming from the 2 sides. So in both terms, they're both going to be 0. Okay? And here, likewise. Here as well, it's going to be 0 because for the same reason. But here, when I do the 1, 1 from this side, 1 from this side, just looking at the 3rd qubit, they're both 1. So I'm left with a 1, 1 1, 1. Okay, and also here we have 1, 1. So that's going to survive. So that's actually going to be a minus next. So that's going to be a minus 2i 1, 1, 0, 1. Here we have 1 and 0, so that's going to go. And then we've got a 1, 1. So it's going to be 2i 0, 1, 1, 1. And here that survives, giving us a 4, 0, 1. Oops. Okay, so that is going to be our partial trace. And if we try and do the same, but now let's trace over the B system. This will leave us with some density operator of the B systems, tracing over A. We're going to have, well, now I need to trace over an orthonormal basis for the A system, which is the first two qubits. So that's going to be like tracing over here 0, 0, 0, 1, 1, 0, 1, 1. And that's an orthonormal basis. So if any of those are different, and this is exactly the same, you're going to get 0. Okay, so so let's just do that here. So here we have 0, 1, 0, 1, so that's going to survive in the trace. I'm going to trace over the A, and I just get left with 0, 0. Here, these two first qubits are different, so that's going to be 0 in the trace. This is going to survive and give us a minus 2i 0, 1. This is going to disappear. This survives and gives us a 1, 1. Here, these are different, so they go 0, 1, 0, 1, so that survives, so we get plus 2i 1, 0. This is 0, 1, 1, 1, so that goes, and 1, 0, 0, 0, 1 gives us a plus 4, 1, 1. Okay, so any questions about that? Is it, so, I mean, once you see it explicitly, I think it's fairly easy. It's easy to see what I'm doing, I think, when you understand why I'm doing it. Well, I'll get to that in a minute. But just so that if I give you a state like a density operator, I think it should be fairly clear now how to calculate. 25. Right, so I've got a couple more trivial examples here, just to explain, just because I want to see So let's just start off with the Bell state. So rho would be the pure state 0, 0. I need to make that a bracket. Plus 1, 1. So that's now that the reason I'm doing this is I want to emphasize that is a pure state, even though the Bell state is entangled itself. Yeah, so this state here, the Bell state, that's an entangled state, but it's a pure state, okay? And it's because the density operator is simply the Keck-Brown of this state. When I trace, so if I say, let's call this rho 1 is the trace over the 2 system of rho, then the 0 and the 1s, this is going to, when I have this term, they're both 0, so I'm going to get a 0, 0. Here I go 0, 1, so that goes, 1, 0, that goes, and 1, 1, and I end up with 1, 1. And this is a mixed state. A mixed state. So this is pure state. And here, when I trace, I get a mixed state. And this has got, of course, something to do with the fact that psi is entangled. So if we just have the pure state and look at the first qubit, you kind of like going, yeah, well, I don't really know if it's in 0, 1, because if we know if we measure here, then we're going to get 0 half the time, 1 half the time. So that kind of makes sense that then this should be the reduced. So this is then called the reduced. This is then called the reduced density operator. So it makes sense the reduced density operator would be a mixed state, and likewise, in fact, this is also, you can publish by symmetry, this is also rho 2. If we trace out in the first system, wouldn't have made any difference. Maybe that's confusing to say that's equal, because of course that's referring to a different qubit, but you know what I mean. Okay, so that's an example of a pure state, which when we do the partial trace, we end up with a mixed state. So let's just see that the other way is obviously possible as well. So here's a mixed state of okay, so I hope you see this is a mixed state. I hope you see the difference now. We're getting used to, because it can be confusing that looks kind of like a mixed state, but actually it's a pure state. Whereas this is a mixed state, right? Because if you think of it in terms of matrices, this is going to be of rank. Okay? You can see straight away this has got rank 2. Okay. And how would it be here, rho 1, if we trace out the second system? Of course, I've set it up in such a way that straight away you see that this is a half 0, 0 from the first term, and also from the second term, and so I'm in the pure state 0, 0. Whilst if I go on the other one, then I end up with a mixed state. This is pure. then this again mixed. Okay, well, I've got another example, but I'd like to move on, and maybe if there's time at the end, we can do another example. So now I want to try and justify this really is. I mean, I kind of gave a vague justification there, but this really is the correct description for the reduced system. So we want to show, so let's just say, so what is row A, which is the trace over B of the density operator on the composite system, the correct description of the A system. So we want to prove that if we do a measurement on A, it will coincide with this reduction. So we want to show that a measurement on the A system coincides with this reduction. Okay, so I'm only going to prove this for projective measurements. So we're going to let M be a Hermitian operator. And consider the projective measurement this defines. But actually, in exercise 3.5, one of you will prove that any measurement could be simulated by a predictive measurement anyway. So this is not too big a restriction to make. So the measurement on, so let me a measurement on the A system. So the measurement on the AB system would be M tensor the identity on the B system. So recall that the average measurement well, let's give it its correct what we use. This was equal to trace n rho. Okay, so that's just for a density operator rho. If we're applying the measurement m as over the average, if we keep producing the same density operator rho, then we will get this as our average. So that's what we proved before. I will go a little bit more into giving examples of how to calculate measurements at the end of today when we look at the uncertainty principle. So measuring on the system A, we would have measuring on A, we get Well, there we have to use the reduced operating density operator, so we get the trace of M rho A. Now, rho A is just this, so this is the trace of M trace B rho AB. Whereas on the whole system AB, if we don't do the partial trace, then we should be measuring M tensor identity on the B. Well, let's write that identity on the B in our one notation. So now what I want to do is check that that's going to give me the set. So I'm going to measure, I'm going to calculate the average measurement of this thing. Okay, so the average of M should be the trace over the whole system of M right. Of course, this is rho AB. Okay. Now, we need if we trace over the whole system, we need an orthonormal basis for the whole thing. So let's suppose A is an orthonormal basis for the A system, and B system. So then this is an orthonormal basis for the composite system. Okay, so we're going to trace over with this. So this is now the sum over A and B of A, B, M tensor 1, B. This all applied to rho A, B. And now we've got A, B going the other way, but we don't change the order because it's still the A system comes before the B system. Okay, and it's this. Now you've got to be, you've got to be a little bit, read this in the right way. This is really tensor together here, this is really tensor together there. And now, what happens, this M is acting on the A system and this identity B on the B system. So this is an identity. So I can pass these B's inside here, and I get this is the sum over the A's of the A, M, and what I'm doing here, I've got the sum over the B's of the B, rho A, B, B, and then again the A is outside. Now the A is outside, so I pass all this on the inside, and then the A here. But what is this then? I mean, this is just tracing over the A system of M, and here we're tracing over the B system of rho AB. Which is exactly what we wanted to prove. Yeah, maybe I should say, I mean, this is obviously tracing over the A system here, because we're measuring on A. So this is why the partial trace, this is a justification for why the partial trace is the correct way to look at the reduced system. Okay, so if you're given, so let's just recall, if you're given like a density operator or a composite system, and you want to know, well, how should I just, if I just think about, if I've only got the, if I'm Alice and I've only got the Alice bit, how should I be looking at this system? And you just trace out with the Bob's particles, and then this gives you the correct description of the particles that you can see. Okay, and as you can imagine, that's an extremely, extremely useful thing. So from all we will hear today, the partial trace is what we're going to see more than anything else, I would say. So if you have any questions, ask them now. Okay, but as I said, we will have time to. We won't probably have time to do an extra example at the end of today. But let's push on. So that was 3 point. Oh, I put 3.7, but actually that was 3.6. I've gone out of order here because I put it on the same piece of paper. So that was 3.6. This will now be 3.7. Sorry about that. And what this is now, what we're going to see now is I don't know, sometimes it doesn't really have any physical interpretation. It's really just a mathematical construct that will be useful for us in the information theory bit. But it's related to partial traces, so we'll mention it now. So this is purifications. And this is, I'll just tell you and then you'll see. Hold on, let's see. Okay. So suppose we're given a density operator row A in system A. We introduce a system R such that and with the same number of qubits. That's A. And we want to find a state on the composite system AR such that the row A will be the trace over R of this pure state. Okay, and so this psi is called the purification. Okay, so it's a completely mathematical construct coming from the definition of partial trace. And the answer is the following. So, given your density operator, it says it's a density operator, it has a spectral decomposition.
Why are we saying that R has the same number of qubits? Like, is there a reason why this, it has to be like this, or we just want it to have the same number, or?
Because our construction is going to work. Which for our construction to work, yeah.
Okay, so like you can only find it if it has at least the same number of qubits. You can always find it only if. Okay.
Yes. So you're saying could you find it on less? Probably, yeah. But yeah, you can at least do it with you only need to add as many as qubits are in A. Yeah. So by spectral decomposition, this row A is the sum of, what have I written there? Lambdas, PIs. PIs because it's a density operator, of course. So these are positive. Yeah. So PI I on the A system I A. Okay. Okay. So just recall, yeah, that we can, where this is an orthonormal basis. Yeah, okay, so that was by spectral decomposition theorem and the fact that this row A is a density operator. So it's positive and traces 1. Yeah? So we can think of these PIs as probabilities. Okay, so we introduce a orthonormal basis for R. Let Y R be an orthonormal basis for the R system, and let okay, and it's simply you stick on the R's to the end of the I systems. And why does this work? So recall what we want is that when we then trace over R of this density operator corresponding to this state, so the pure state density operator corresponding to this state, we should get that row A. Okay, so let's just check that. So we don't need any of that now. So this is our purification. So this is the purification, a purification of row A. So let's just check. So we've got to calculate the trace over R of this thing. Well, that's going to be the sum over Ij of square root Pi Pj I A I R J A J R. Trace. Let's just get rid of trace then. So this is that. And now, when we trace over the R system, what happens? Well, you can see what's going to happen. All of these terms here, when I'm tracing over the R system, are going to give me 0 unless I is equal to j, because this is an orthonormal basis. So all I get was here is the sum over Ij square root Pi Bj Ia Ja, and here I get my Kronecker delta Ij. So it's just going to be zeros unless they're the same. When they're the same, so this is just then the sum over I, Pi, Ia, which is right. oh yeah, I have. They're just very small. So, for example, and again, when you see a couple of examples, you just, it's even easier than the partial trace. So here's a couple of examples. Let's say we've been given this mixed state on 1 qubit. And we want to purify it. Well, then so here they've been kind to us, haven't they? Because this is already in its orthonormal decomposition. Okay, so this is already in its orthonormal decomposition. So we don't have to do anything more than just look at the basis, the orthonormal basis here, the IAs, is just going to be, so this basis, let me stress that. So IA here is simply the basis 0, 1. So according to this, all I need to do is stick on the same thing on the next one, 1 over square root 2, that's the probability of 0, 0, and then stick on the R basis afterwards, 1, 1. And so we get the Bell state is a purification of this mixed state. Oh, I made a mistake there. I did have another example, but I realised I didn't have it at an orthonormal basis. And if I do that as an orthonormal basis, then suddenly I have to do a little calculation. Otherwise, it might be right. Oh dear. I think I'm going to leave that because otherwise I'm going to get that wrong. Okay, so that's. Oh, well, maybe we could do it with a blackboard. Maybe not. And the thing is, if you just write up a random density operator, you then have to diagonalize, you have to do the spectral decomposition to be able to then simply stick on, and then you just stick on the end of the thing. So the other basis, the other orthonormal basis. Yeah. So while we're talking about this, let's just do an observation here. There should be something ringing bells about the Schmidt decomposition here, because it does look somewhat similar. So if you recall, for a pure state, on a composite system, the Schmidt decomposition was I of lambda I A I B. Okay, so we could find these orthonormal bases where V are orthonormal bases. Now, if we take the reduced density matrix on the A system, so if we trace over B of this thing, what will we get there? Well, let's just skip a bit because it's pretty similar to how it was before. We're just going to get lambda I conjugate I A I A. Okay, as in this last example. And interestingly, the row B will have the same eigenvalues. Okay, so and the description here does not depend on the orthonormal basis IB. So therefore, this one does not depend on the orthonormal basis of the A system either, which implies that these lambda I conjugates do not therefore depend on which orthonormal basis you use here for the Schmidt decomposition. Now that also follows from the fact if you to do the Schmidt decomposition, we had to use a singular value decomposition, and these values were the unique being the eigenvalues of GA matrix, which was A Hermitian A. But it's a nice observation to make there. But the important thing that we will use later is that the reduced operators have the same eigenvalues. Note. And that will be very important for us later. Okay. So that's probably all I'm going to say about purification for the moment. If there's no further questions, I'm going to go on and talk about two very famous and important results in quantum mechanics. The first is the Bell inequality. And in both cases, they tell us really that nature isn't the way that we think it ought to be, and it's giving us very good evidence for our interpretation of quantum mechanics is correct. As I stressed before, I mean, we talk about these probabilities and we talk about this as if it's like the way it is. We don't really know it's the way it is. It's just our interpretation, and for the moment, it's backed up by experimental evidence. Okay, so it does appear to be the correct way. I will stop. I will talk a bit more about that after I've talked about these two things, and that will then complete this topic, and we will move on Thursday to get back to the circuits and start computing some quantum circuits and stuff. Okay, so that'll get a bit more exciting, a bit more hands-on. This is the famous Bell inequality, and it works the same in this way. Okay, so So let's imagine that Carlos prepares two particles gives one to Alice and one to Bob. Alice and Bob, Alice chooses with 50-50 probability 1/2 between experiments. Let me use the same letters as I used here, otherwise I'll get lost later. R and Q, each of which has results plus or minus 1. Okay, so she chooses with 50% probability, I'm either going to do experiment R, which is going to give me a result plus or minus 1, or I'm going to do experiment Q, and that will also give me result plus or minus 1. And so it says here that you can think of like maybe Carlos gives her a ball. It's dark, and she one experiment maybe shining a light on it and see what color it is. Okay, it's either she knows it's either going to be red or blue. Yeah, with probability. And suppose Bob does the same, but with experiments T and S. So we have 4 random variables, R, Q, T, and S, each taking the value plus or minus 1. With probability 1/2. Now what is, and this is the clever bit, Q plus R, what are the possible values for Q plus R S plus Q minus R 2? Here I put R minus Q, but I don't think it makes any difference. Well, let's put R minus Q because otherwise later it will go. Okay. Okay, so I think the idea here, I didn't go over this beforehand, but I should have. I think the idea here is that Bob will choose between experiments S and T. Okay, so if it's S, then this is going to be plus or minus 1, and this is going to be plus or minus 2, and likewise, no. Yeah, Q plus, if Q is 1 and R is 1, these are either both plus 1 or minus. I get it now. Yeah, I got it. So these are either plus 1 or both minus 1, or they're the same or they're different. If they're the same, then this is 0. And these two are different, so I get plus or minus 2. Yeah? So let's write it down. Yeah? So if Q is equal to R, then this is 2RS, which is equal to plus or minus 2, obviously, because this is plus or minus 1, this is plus or minus 1. And if Q is equal to minus R, obviously, yeah, so this is going to be 1 plus or minus 1, so this is either going to be Q is not equal to R, then this is going to be, then it's 0, then this is plus or minus 2RT, which is plus or minus 2. Now let's say the probability now the expectation of QR plus QS plus RS plus RT minus QT, which is this thing, is the sum over the small ones of this P, Q, R, S, T times Q, S. And now by linearity, yes, well, this quantity, of course, we know is either plus or minus 2, so this is at most 2. So by linearity, this implies that S, R, S, R, T. Okay, so up to now, there's no quantum mechanics here. That's just simply a classical application of linearity of expectation to some random variables. But now suppose that prepares the state and Alice performs on the first qubit. The observables, Q is going to be Z, and R is going to be X, whilst Bob on the second qubit is going to perform. So let's put the ones down here just to remind ourselves. 2. we know how to calculate these expectations, because this is just a projective measurement. So let me calculate one for you. This will be homework for somebody. But we can calculate QS. This will be the average of this observable is. Note that they are Hermitian. Well, they are Hermitian when we put them together. Yeah? Is psi. So this will be Z1 minus Z2 minus X2 divided by root 2 psi here. Okay, so we can calculate this. I'll do this one for you and you'll see, and then I'll tell you what happens to the other ones. So when you calculate this, we're going to have, let's do psi here, Z1 minus Z2, so let's take out the root 2. In fact, that's going to be a half now because we've got I'm going to substitute in as well this psi here, okay, for the cake. So we're going to have half that, and now I want to do minus Z1, Z2. So minus Z1, Z2, so remember Z1, I just flips the sign if there's a 1. So there's no 1 here, but there is a 1 there, so that's going to be minus 0, 1. And minus Z1, Z2 on here, well, that's going to give the plus and then a minus here, so that's going to minus 1, 0. So that was the minus Z1, Z2 on this term. Now I've got minus Z1, X2 on this term. So the Z1 doesn't do anything on 0, but the X2 flips the 1 to a 0. So I've got minus 0, 0. And now I get a plus with the Z1, X2 on the final term. The Z1 flips the sign again, so it goes back to minus, and I get a 1, 1. Now I've got to substitute this side. And just see which term survives. So it's going to be the 0, 1, and if I do the bra of this, I get the 0, 1 and the 1, 0, which are both positive, so I get a positive, sorry, a negative, and then a positive, and I got 0, and I shouldn't have. So something went wrong. Hold on. 0, 1. The first one is a positive apparently. So I've got a minus here. There's a positive here, but then I get flipped by the Z2 and that becomes a positive. Okay, so that is a positive. Okay, so this is this minus, but then I get a minus from the Z2 on the second qubit here. So I get 1 plus 1. And I've got another root 2 coming from this root 2 when I substitute here. So I end up with 1 over root 2 and a 2, which is 1 over root 2. And it so happens, and it will be one of the exercises, to show that the other ones are this is also RT is equal to 1 over root 2. So this expectation here is 2 times the square root of 2. Now, clearly something has gone wrong because we just proved that this expectation to some of these points for expectations is at most 2. And now we've proved that it's 2 times the square root of 2. And the reason being is that we made some assumptions when we proved this bound. And one of the assumptions we implicitly made was that, for example, Alice's measurement does not affect Bob's measurement, which is kind of logical because you don't think it does. But of course, in quantum mechanics, it does, as we've already seen many times. Okay, so that's one thing that's wrong. The other thing that's wrong is that we assume that physical properties actually have definite values and independent of observation, and that's also not clear in quantum mechanics. So this, let's call this star and double star. So the question is, which one's right? So experiments reveal that double star is correct. Yeah. So you can get better than this expectation of 2, and so the assumption that what's wrong is that well, let me say what it says in the book. Okay, so locality, Alice's measurement does not affect Bob's. And reality, that physical have definite values regardless of observation. One of these two things must be wrong. And in fact, we've been assuming both of them are wrong since the very first day. Yeah, it's just more evidence to suggest that what we're doing is right. So Einstein was definitely not happy about our interpretation of quantum mechanics, but this was further experimental evidence to the case where you really have to accept it, at least until somebody comes up with a better theory, a better interpretation. Okay, so that's Bell's inequality. And now we're going to move on to one final consequence of our interpretation of quantum mechanics. And this is the Heisenberg uncertainty principle. So I'm just going to prove the bound, and then we'll look at some examples and check that it works. Okay, so let's suppose A and B are two Hermitian operators. Now recall at some point we observed that that does not imply that AB is Hermitian. Okay, so AB, for example, so this does not imply. For example, we observed before that XY is IZ or something, and therefore not Hermitian. This is Hermitian. This is not. Yeah. Anyway, so therefore, if I calculate for some state psi, this is going to give me some complex number. Okay, so I have to write that as a complex number. And if I look at the conjugate of that, then this will be BA minus Y. Which implies that it's 2i. Yeah, so if I now take this and look at its conjugate, this is going to be this with its conjugate, which is 4y squared, which is less than or equal to 4 times what I would get if I conjugated this thing here. So okay, because that's x, this is x squared plus y squared. Now, if you think about Cauchy-Schwarz, so we have U, V. Let's do it like this way now, yeah? Let's put U is equal to A psi and B psi. Then what we have here essentially is this side of Cauchy-Schwarz. Yeah? So here we just have this. Well, let's write this differently. Let's write this as it should be. Yeah. U. Then this is this bit here. Yeah? This is UV, and this is going the other way here. This is UV conjugate. So we have this implies. So this implies that. So putting this together, we have that. And here I'm using the notation for the commutator of A and B, so I'll just tell you this is this, where Now that is basically the inequality we want. We just have to do a little recalibration of our Hermitian operators A and B. So just recall, this was the average of A. Yeah, so this was the expectation. So that was for a fixed state psi A psi. Okay. So the average of A squared is obviously A squared. And you will recall that the variance is the expectation of A squared minus the expectation of A breathed squared. And so, and the standard deviation of a random variable, well, of course, we're still using all the same. And the standard deviation, is the square root of the variance. Okay, so what we're going to do is turn this inequality down here into an inequality of the standard deviation of these two measurements. So we just do a minor adjustment to make the average of the random variable 0. So this is actually going to be a form for C and D. So this, oh sorry, the other way around. Sorry, A squared is going to be C squared minus C. Which implies that the average of A squared is the average of C squared. Now we get minus twice the average of C squared plus C squared. So you get minus C squared, which is the variance of C. Okay, because when you do the average here, this is just a number, so this minus 2 comes out and you get the average of C. And you can see the average of C times the average of C is C squared, minus 2 plus 1 is minus 1. So you see down here, this is really nothing more than the standard deviation of C squared. And here we have the standard deviation of D squared. And all we need to do now is just calculate what is the commutator of A and B in terms of this. So that's AB and it's fairly quick to see that in fact, apart from the CD and the minus DC, all the other terms are going to get killed by the something in the other by the minus here, because everything commutes now. I mean, this is just a number, so this is some number. This is brackets average C times D here minus, and here you have it plus. This is minus average D times C, and here you have plus average D times C. And final term is just the average of C average D minus average C average D. So this is just CD. Commutator of CD, and we have arrived at Heisenberg's uncertainty principle. So this implies that Okay, so I just substitute the fact that this is the average of A squared, this is the average of B squared, and this commutations don't change. Sorry, I missed, I don't know how this happened, but this should have been this. I'm not quite sure why I made a mistake before, because now I've rubbed it all off, but at some point I must have copied that down wrongly, okay? So this is this squared, because then you can take square roots. So this is this squared, and now we take square roots, and we end up with the square root of C. Sorry, the standard deviation of CT is bigger than 1/2 of this thing. And that's the uncertainty principle. So what it says is, and the reason it's important is it says, well, I can repeat the same experiment, knowing exactly, preparing everything in the state psi, and if my Hermitian operators do not commute, then there will be some. So the more accurately I get the results from C, the less accurate, the more I will get, the more deviate from the D. Okay? So the classic Heisenberg uncertainty principle, one of the C is the position operator, and the D is the momentum operator. Okay, so that means that when you measure with the momentum operator, it gives you the momentum. When you measure with the position operator, it tells you the position. And there is these two Hermitian operators do not commute. In fact, their commutator is I times the reduced Planck constant. So you get some uncertainty between the two. You can never be sure about both the position and the momentum, which Einstein again didn't like, because it meant that physics will not, if you can recreate exactly the same conditions and from the same initial conditions, you cannot say what the system's going to be. Okay? There's always going to be something fundamentally uncertain in your prediction. Okay, so let's now just see if I can calculate an example. Yeah, so first I wanted to do an observation. What time have I got? Yeah, I think I've got time. Okay, so here's an observation. So what I wanted to do was try and prove this was wrong. So I thought, well, what happens if we try and find some C and a state so that the standard deviation is in fact 0. Okay, so if I do that, then so anything that commutes with it, then yeah. So let's say C is Hermitian, so it has spectral decomposition. And let's suppose our psi is one of the eigenvectors of this C. Okay, so what is so C times psi is in fact just lambda I psi I. Sorry, psi. Well, psi. And so our size is lambda I squared. Oh, lambda I. Oh, sorry, no, it's just lambda I. It's just lambda I because now let's keep it on. I'm getting myself confused. Okay, because then I just get psi I, which is a unit vector, so I just get the lambda I. And C squared, this is just applying C again, so I get lambda I squared psi I. And so this implies that the average of C squared is going to be lambda I squared, which implies that the standard deviation is 0, of course. If I keep giving it the same eigenvector, it will keep so I wanted to make some observation about the fact that, of course, C and D commute. So recall from exercise 2.3, C and D commute if and only if they they diagonalize in the same set of D is, well, basically D is also mu with the same satellites, right? So, but what I'm confused now because so this actually just means that the average of the commutative C and D is whatever is always going to be 0, right? Because now we already have 0 here. So I was just going to observe now that if you get something which commutes, of course this is 0, and you get 0 here again with the lambda D. So if they commute, you will have the same thing for this. This will now be mu I squared minus mu I squared, which is also 0. But that doesn't actually, I mean, I've already got 0 on the left-hand side anyway, so I'm not quite sure what I wanted to say there. I was just trying to play devil's advocate and find a 0 here. Well, I suppose what it means then is whatever emission operator you take D here, when you take the average of the commutator, it will always be 0, just because this psi I is an eigenvector of the C. Okay, so I'll leave you to check that. So this should imply, so that's just another observation, but so this implies that well, this of course now we think that psi I is up to 0 or D, so we can check this. Right, so I think I've just about got time to do my example. I wanted to do some calculations. I promised you I was going to do some calculations last time and didn't get round to it, so now I'm going to do it with and calculate a bit of this inequality as well, in which case when it's not 0. So I'll just leave it up there. And I'm going to try this Hermitian operator, and I'm going to write it as a matrix just because it's a little bit easier to do the matrix multiplications rather than writing out as the 0 ones. So let's take that to be our Hermitian operator, and our ket, which I'm just going to write as a normal row vector, a column vector for the purposes of this, is going to be okay, so, and the reason I've chosen this ket is because 0, 1, sorry, 1, 1, yeah, if this is 0, then this is 1, 1, and 1, 1 is oh, sorry, I've copied that down wrong. This is minus I. For the same as 1. 1 minus I, so let's just say observe 1 minus I is an eigenvector. Well, in fact, it's in the kernel, isn't it? Is in the kernel of C. Okay, so this is going to give us something which is very, very, very short vector. Okay? This is not a unitary matrix. This is not preserving unit distance. In fact, C times psi, this should be something quite short. This is e to the I plus I squared, I e to the I psi minus I. Okay, so if you calculate that length, it will be quite small. And so what we want to know is what is psi c psi. So now we have to take the 1/2, take the bra of this. So this is going to be, that goes there. And it should just give us a real number. So that's 1 minus e to the minus I theta. And then I down here, minus e to the I theta, minus I squared, which is plus 1. So I get 2, 1/2 of 2. And here, so this is cosine theta minus I theta, this is cosine theta plus I theta, so I get minus 2 cosine theta. And remember, we're taking theta to be small, so this is almost 1. So 1 minus this is almost 0. So that's just calculated. So this is the average of C. So now let's see what the average of C squared is. To do that, we don't actually have to do very much, because observe C squared is equal to 2 times C. Okay? That's because, in fact, the easiest way to see that is that we've already established that there's something in the kernel of C, so we know that 0 is an eigenvalue. And the other eigenvalue, well, you can see that if this was minus 1 and minus 1, then this would be 1 minus, well, the determinant would be the same as it was for C, and the determinant of C is 0, so just change it. So if we subtract 2 from the diagonal here, we still get a rank 1 matrix. So therefore 2 is the other eigenvalue. So the eigenvalues are 0, 2, so the minimum polynomial is x squared minus 2x. You see? Good. So that's just that you don't actually have to calculate c squared. So c squared is 2c, and the average of c squared therefore is 2 times 1 minus cosine theta, which means that the variance is 2 2 1 minus cosine theta minus 1 minus cosine theta squared, which, if I did this correctly, is 1 minus cosine of theta all squared. 2 minus 2 plus 2, yeah. Okay, so that's given us a quick way of finding, so that we've managed to quite quickly calculate something. And we could do a d, so let's introduce a d and do the same thing for that. So I wanted to think, well, what's another way of getting something which is going to be small here? So I thought, let's get rid of, so I need some space. I'm going to get rid of this bit. This calculation, here we go. So let's say d is 1 minus I minus. Right, and let's do the same thing. So then we get that d. So now we get e to the I theta minus plus I squared minus e to the minus I theta here, and below we get I e to the 2I theta minus I, and now we can calculate the average of d. We're going to have to 1/2 kept that, bra, sorry, and yeah. And this is going to give us 4 terms again. We're going to get 1 minus e to the minus 2I theta minus e to the 2I theta minus I squared, which is 1. And this is exactly the same as we had before, so we can now skip all the way to the end because everything is exactly the same, just replacing theta with 2 theta, and we conclude that the variance of d, no, you also, no, because we have to check that d squared is also, so let's just check first that it's got 0 determinant. Yeah, so if you take 1 and then you take this, you've got minus a minus I squared, and this times this is 1. Okay, so I chose this cleverly again so that d squared is in fact 2d, because this determinant is 0, and if you change this to a minus 1, it's again still determinant 0, of course. So again we have this, which implies that everything is the same, and then we can conclude that the variance of d is 1 minus cosine 2 theta all squared. So conclusion, this quantity here is very small. It's simply 1 minus cosine. Let's do this square. Okay, so it's approximately 0. Okay, so this is approximately 1 minus 1 minus approximately 1. So it's very, very small, which from Heisenberg's consensus principle means that this thing here is going to be very small. So let's just see what happens. But of course we know already, since they've got the same, let's just check it. So now I can get rid of sine, I don't need anymore. we can check that C times D is, I do need psi, but it's still positive, still positive. Still positive in its bra form. So CD is 1 plus e to the I theta. Here I've got minus I to the minus theta minus I. Here I've got I plus I e to the I theta. And there e to the minus I theta plus 1. And DC, well, now how do I do that? The other way, it's going to be 1 plus e to the minus I theta minus I e to the minus I theta, I to the e to the I theta plus I, and finally minus I squared, which is plus e to the I theta plus 1. So when I look at the commutator, this in fact just this times this minus this, which is this is cosine plus I sine, and this is minus I sine, so it's 2I sine theta 0, 0, minus 2I. Which of course is very, very small because this theta is small, yeah, so this is almost 0. And I believe that if you check, because I checked this before, then you actually get the psi CD minus DC. Is E what am I missing? Yeah, I'm not quite sure about the eyes, but there might be an eye outside. But you can check yourselves, but I think this comes out to be 0. Okay, so possible. Anyway, right, so I think I've just about got time to talk a little bit. So that's all I wanted to say about the uncertainty principle. So I hope that's helped a little bit with the calculation, so you see just how to calculate averages given a Hermitian operator and things. So now the plan will be to start on Thursday with the new section on quantum computation. So we're back to the circuits and calculating things. And one of the aims will be to try and have like a kind of, our first aim will be, we saw in the exercises in the introduction that we could find a nice small set of gates which would be universal gates for classical circuits. So our first aim will be to do something similar for quantum circuits, find a small set of universal gates. And then on Tuesday we'll do the exercises. Now I was looking at the exercises and I've divided them up. I will send that list out after the class. I thought it might be a good idea though. I was looking at it thinking exercise 10 is a little bit difficult if you don't realize something. So I will just, and this is probably interesting for everybody, so not just those that have exercise 2. So imagine, so let's just imagine, so suppose sigma is Hermitian. So I'm thinking sigma because I'm thinking it's a Pauli matrix such that sigma square is the identity So its eigenvalues are plus or minus 1. So this is about exercise 10 really. Values are plus or minus 1. So what are the projectors? The plus 1 projector is 1/2 I plus sigma. And the minus is the projector onto the minus 1 eigenspace is this one. Why? Well, in fact, very easily I can show you why, because P plus, let's just stop dropping ones and call them P plus and P minus. P plus plus P minus is indeed the identity, and we know that sigma should be the sum of lambda P lambda. And so that should be plus 1 of P minus P minus, and that works, right? So if we take them away, then we get sigma. So check. Okay, so why am I telling you this in relation to the exercise 10? Well, remember that the king in this exercise is going to apply a measurement which is one of the Paulies. Okay, so after the measurement, the state psi gets left in some eigenstate of the operator. Yeah? So that's either plus or minus psi. Okay, so it goes to one of these two. So recall that this is going to map you. This is a linear map which maps onto the plus 1 eigenspace. And this is a linear map with minus 1. So the result after the measurement is always leaving yourself in an eigenstate of the Hermitian operator. Alternatively, you could just think of it as a general measurement, in which case, in the case of a projective measurement, the measurement operators are just the projectors, right? So P plus, P minus, and therefore, if you choose the plus one, if it's the plus one, then it goes on to, if you get the result 1, then it goes on to P plus, and if it's minus 1, then it's P minus of psi. Okay, so that should help you a little bit to determine what to do with that exercise. So when the physicist gets the qubit, it's in one of these two states. Okay, I hope you're listening, Adrian Edgar. So when it's we'll watch the video later. All right. So I'll stop there. Are there any questions? Just to say that I've kind of fixed the date of the exam, or at least if it's okay with everybody, because of the guys from some of the guys have other exams on the obvious Tuesday and Thursday, which would be the first week of April. They can't do it then, so I thought we could do it on the 13th of April, if that's okay with everybody.